Okay, very good. Thank you. Anyway, it's today is good morning again. Today is Thursday, March the 18th, which marks exactly 1 month from the day we started the spring semester. Today is actually, what is it? We're supposed to have an exam in about after 2 weeks, there is a spring break. Then after that, we will have our exam. So we still have 2 lectures actually to cover. And the 2 lectures are from chapter 25 and chapter 26. Chapter 25 deals with the concept that we have introduced already, namely the concept of battery and what it means and the electromotive force and things of this nature. And then we introduced the resistors there. So we're going to have how to calculate resistors and everything else. Chapter 26 deals with how to take resistors and again combine them in a series and also in a parallel configurations. Now the thing with that is that we needed actually the concept of current more in depth than what we have introduced it in this chapter. But the point being we're going to get there, and hopefully by chapter 26 we will have that. And there is a big deal from chapter 26 coming, and that is going to be the charging and the discharging of a capacitor. So in a sense, we will have an RC circuit, a circuit where we have resistors and capacitors in the same time. And that is going to be the end of basically the first half of the course, where we are going to be dealing later on after the exam, after the midterm, we'll be dealing with chapter 27, where magnetism is actually introduced for the first time, and go after that to finish the course from chapters 27 to 32. So this is in a nutshell what his class is. I know some of this class are sitting in another class I'm teaching, namely Physics 4C. And in Physics 4C, yesterday, something wonderful happened where actually we made 2 mistakes in solving the problems. And that is good because in a sense that making mistakes is a human, that is normal, okay? So when you're solving problems and then all of a sudden you find that you made a mistake, don't panic. You have to develop a skill though to recognize the mistake right away, okay? To recognize that you really don't need to go further, that you have made a mistake, okay? So that was the big fuss in that class yesterday. And when they happen like this one, it's great because, like I said, making a mistake, that is everybody. Whoever says doesn't make mistakes is a liar, okay? Doesn't matter who they are, okay? Recognizing that you have made a mistake first and fixing it, that is a skill that you really need to develop. If anything you take from this class is hopefully how to problem solve stuff and how to work your way and recognize, does the answer make sense to you or not? So this is basically the goal of this class, because at the end, the concepts, you can Google them and you might find them, and even the solutions, sometimes you find them. But if you are in the field working problems, then you're on your own, okay? So you're on your own and you really have to rely on those skills to do that, okay? So nobody's going to help you with that. So that is what I'm hoping to achieve with you guys, okay? Okay, and then the other thing also, okay, I'm looking at problems in here and I don't know how to start them and all of that. That is again a skill, and that is only can be overcome by doing more and more problems. And that is the purpose of this sessions that we're having together. We're dividing the lecture into 2 halves, basically. Conceptual lecture, where we just basically talk about concepts and we go about the theory and things like that. But that's all fine and dandy. But when you go and turn on the next page where the problems are, usually it's hard to start these problems. And the reason why it's hard to start these problems is because you need to practice. You need to start following and seeing how they are done, so that you're empowered with a battery of tools that once you have a new problem, you look at that basically bag that you have next to you and you start picking up the tricks, if you wish, of the trade. Does this one work here? No, this one, maybe that one, and maybe a combination of these 2, bang. And you start thinking of the solution, okay? So again, like any other problem, the first step is reading the problem. Let me first of all pull my notes in here. and create a new tab, and the new tab is namely chapter, let's make caps, okay, chapter 17, problems. And let me share with you the screen, share, screen 1. Are you guys looking at chapter 17 problems? Yes.
Yeah, it says chapter 17.
Yeah. So the problems we thought we will tackle today are the following. Problem 1. Okay, so that you think that we can't handle difficult problems. We always go to the problems 100 or 70 or 60. So we should be able to handle difficult problems like problem 1. Problem 1 is very important problem though, because it's really a practical problem. So you really have to think in terms of that. Okay? Then we're going to jump to 51. And then we're going to, in doing problems, the rest of these problems, we're going to follow the advice of Marcella, which is a really wonderful one used by everybody working electricity. So we have to do that, okay? Namely that we're not going to be tinkering around a lot with the micro and the nano and all of that stuff, okay? Just do them at the end. So good morning, the rest of the people who just joined us, okay? Again. Anyway, 53 is the other problem. I hope that you guys have a piece of paper and a pen or a pencil, and you are not just relying on me, watching me basically, and probably playing with the phone, or maybe even have the game going and watching it, because that's what I really want to do today. I know there is a big game in the afternoon around 1 p.m. Okay, but you're actually doing these things, okay? The UEFA games, if you really are following the soccer stuff. Anyway, problem 57, problem 59. I think that's enough for today. If we can manage to get 1, 2, 3, 4, 5 problems, I think it will be in good shape. Okay. And don't forget, we have lab this afternoon. That too is going to touch on a lot of these things. So we have an important session at 5 p.m. today. Don't miss it. Okay. So problem 1. Problem 1 says basically that we have the plates of a parallel plate capacitor are 2.5 millimeter apart. So here is what you could do right now is you could go to your kitchen, bring some aluminum foil and make cut out of it, at least separation of 2.5 millimeters, which is kind of a piece of hair, okay? Slightly thicker, okay? So that's how far they are apart. So what you do in this case is a piece of paper like this one and stick it in between them. So that's going to insulate them. Otherwise they will touch. So they're not going to really act as a, so that's going to be your dielectric, okay? So a piece of paper is going to act your dielectric because it's insulating, and in the same time is going to separate the two sheets. So basically, that is what we're looking at. So so we have, again, the separation between them is 2.5 millimeter, and each carries a charge of 80 nanocoulombs. So there is a Q of 80 nanocoulombs sitting on them, okay? So this one is positive, by the way. This one is your negative. So this one has a negative 80. This one has a positive 80 coulombs. But sigma itself is actually equal to Q divided by A, where A is this area. So when you're going to get your aluminum foils from the kitchen, you really have to have a specific area. At this point, I don't know how much area because they didn't tell us, okay? The plates are in vacuum. So this problem is not going to work for you. So if we're going to take a piece of paper and put them in there, so it's not going to work because they're not. This is not vacuum. This has its own permittivity. Okay. But if you do remove the air and just keep them 2.5 millimeter apart, that is basically the problem we're dealing with. Okay. The electric field between the plates has a magnitude of 4,000 or 4 million volts per meter. So remember the electric field between the plates, E, which is sigma over A, sigma over epsilon naught, that value is 4 megavolt per meter. Remember, we were using Newton per coulomb for the electric field, but then we have a definition for the electric field using a voltage, which is a voltmeter, just like this guy, okay? And also the battery is in volts, everybody is in volts, and the separation, which is in meters. So you have 4 million volts per meter, okay? So that is basically megavolt per meter. So that is the electric field, tremendous electric field, yes. So what is the potential difference between the plates? Okay, we know that the electric field and the potential are related to one another via that expression at the end in magnitude, okay? Which is this potential is higher than this one. So if this is V equal to 0, this is exactly V, okay? So, and the electric field is pointing this way. So if I do calculation, the integral from the up to bottom, so it's going to be E dy from 0 to D, but then don't you forget this one. So at the end, the voltage, when you take account of the signs again, this is where Y is pointing, okay? So when you do the algebra in here, this is going to be because E is down, dy is up, but there is a minus in the definition to begin with. So the minus times minus is positive, and at the end, it's E times Y, integrated between 0 and D, which is just D. So this is the voltage. So it's straightforward. All we have to do is multiply 4 million times 2.5 millimeter, and we're done. So part A then, the voltage is going to be 4 times 10 to the power 6 times the distance, and distance is 2.5 times 10 to the power -3 meters. So 10 to the -3 and 10 to the power of 6, that's 10 to the power of 3. 2.5 times 4, that is 10. So this is 10,000 volts. Okay, tremendous voltage. So basically plug it. Of course, if you use this experiment at home, you're going to run into a problem. You really have to have a big transformer, okay, to take the voltage of 120 volt and up it up to 10,000. So it's not going to work if you're going to do this very same problem at home with in the kitchen. But don't forget, 10,000 volts is tremendous voltage. So you have to be very, very careful with that voltage, okay? So this has to be done in a contained environment, in a controlled environment, like in a laboratory with a specific equipment and things like that, okay? But if you want to have fun and see how it looks like, bring a battery or two, and that's going to give you about, if it's 1.5 battery, 1.5 volt, bring 4 of them and you already have 9 volt. So you're not going to have this tremendous electric field, but you will have some between the two aluminum foils, okay? So you can do that. So this is doable, 100%. Okay. So the potential difference between the plates, the area of each plate. Now we know what Q is. We know what the electric field is. And remember, the electric field is sigma over epsilon naught. So E is sigma over epsilon naught, which is equal, sigma, remember, is equal to Q over A. So this is going to be Q over A, and don't forget the epsilon naught. So we have E, we have Q, 80 nanocoulombs, we have epsilon naught, so we should be able to find the area. So the area A is going to be Q over E times epsilon naught. So this is straightforward substitution in here. So the area A then is equal to 80 nanocoulomb, okay, 80 nanocoulomb, divided by the electric field, which is 4 times 10 to the power 6. And I need the value of epsilon naught, or 1 of the epsilon naught to be more specific. I know 1 over 4 pi epsilon naught, that's what I memorize, okay? It's 9 times 10 to the power 9 SI. Just like you memorize G is equal to 10 from physics 4A, this is a good number to remember. 1 over 4 pi epsilon is equal to that, which means that epsilon naught itself, or 1 over epsilon naught itself, is just 4 pi times 9 times 10 to the power 9, okay? So if you remember 1 over 4 pi epsilon naught, you can find its inverse. Remember, epsilon naught itself is a very, very tiny number, which allows for its inverse to be a very, very, very big number. That's all, okay? So we need that number in here. So what that number is then, and this is where the mistake I see from people in the first exam, what they do, okay? In the first exam, typically in here, they sub the value in the denominator, which is naught. It should be in the numerator, because you're looking at 1 over epsilon naught being equal to that number, not epsilon naught equal to that number. So you sub it in the numerator. So exam 1, I see many people get basically thrown off by this number epsilon naught, and they will have ridiculous values for the areas or the electric fields or whatever they're calculating, or forces or something like that. Forces that if you put them on the scale of the universe, they will become either astronomical values that cannot be sustained in the universe, or they could be lower than anything else that you can find, an area that is less than the Max Planck's basically distance, which is ridiculous. It doesn't exist. It's not physical at all. So you will find the ridiculous values in there. But again, make sure it's 1 over epsilon naught, so you put it upstairs, not downstairs. I mean, the value, it's the inverse of epsilon naught that is equal to this value, not epsilon naught itself. Now, having that, then we can do some algebra in here, because we need an area in meters. So this is going to be 10 to the negative 9. That's what the nano is. And 10 to the power 9, they cancel. And nicely in here, I'm going to put the A, which is going to be, I have a 4 in here and a 4 in here, and 10 to the negative 6 in here. So everybody's happy. All I have to do is multiply 80 by pi by 9, and it's going to be 10 to the negative 6. Okay? So that is basically, let me see, what is my calculator? So what we have in this case is 80 times pi times 9. That's all there is to it. Okay? Did I miss something? 80 times 9 times, the 4 is gone. Okay. So this number is 2,261, or 2,260 roughly, okay, times 10 to the negative 6 square meters. This is an area, which is a very tiny area. So now, remember, a 10 to the negative 2 meters is a centimeter. So when I square this number, 10 to the negative 4 meters is actually, meter squared is equal to a centimeter squared. So if I divide by that number, I'm left with this. So it's going to be 22.6 centimeters squared. Okay, that's a more reasonable number to work with, okay, than actual meters. So if you're going to making this from aluminum at home in the kitchen, make sure if you're going to use it a square basically shape like this, this height in here and this height, this width need to be square root of 22.6, which is roughly how much if you're going to do it at home in centimeters, of course. Okay, 22.6. I'm sorry, square root. I forgot to square root that number. Square root of 22.6, which is about 4.8 centimeters, 4.75 centimeter. Okay, so take a ruler like this one. Where is my ruler? What happened to it? Is it somewhere? Make sure it's in centimeters, and it's about 4.5 centimeters, slightly less than 2 inches. Okay. No, this is about 4.5 centimeters, and another 4.5 centimeters, separated by 2 millimeters apart, 2.5 millimeters apart. Very tiny distance. Okay, about 2 inches by 2 inches. Separation is 2.5 millimeter. So that is your capacitor. Okay, provided you can put that much voltage on it. Okay, which is going to be hard. The other way of doing it is just take piece of plastic and start rubbing it against your cat and build a lot of charge on it and discharge it on both of them, though you have to have very good technique on getting the charges to be equal, because you can't put 80 nanocoulombs in here and 0 on the other side. That's not a capacitor, okay? So you have to make sure you take it from one side and put it to the other to make sure that that works. With a battery, it works beautifully because the battery is connected to ends. One side is going to be negative, the other one is going to be positive. So it's much easier to do to the battery. Makes sense so far?
Yes, Professor.
Very good. So part B, now part C. Part C, it says the capacitance. Now we need to find C. We have two ways of finding C now. Let me tell you the two ways. First one is by definition. Remember, V is equal to Q over C. That means that C is equal to Q over V. We have Q, which is 80 nanocoulombs. And we have V, which is 10,000 volts. V is 10,000 volts. That's from part A. So all you have to do is just do the ratio. This is volt. 0 cancels 0. And I have 80 nanocoulomb divided by 1,000. That's actually 8 picofarad. Okay? Because we move up. So it was a nano. Now we went to 10 to the negative 12. So it's actually picofarad. Okay? This is the number we're going to be dealing with this afternoon in the lab. Now, the other way of finding it is actually going to the formula that we use. Remember, we have A times epsilon naught divided by D. This uses a geometry. A, we found it to be this number. You have to make sure it's in the metric system, okay? 2,260 times 10 to the negative 6. That is in square meters. Now, time is epsilon naught. Here's the value of epsilon naught. Epsilon naught is, by itself, 1 over 4 pi times 9 times 10 to the power 9. Okay? That is how I memorize it. You may have already access to its value. So it's going to be in the denominator now. It's 4 pi times 10 times 9, I'm sorry, times 10 to the power 9. And then you have D. D is 2.5 millimeter, which is 2.5 times 10 to the negative 3. Okay? So you have a 10 to the negative 6 and 10 to the negative 3. So it's 10 to the negative 3 upstairs. When you take 10 to the negative 10 to the positive 9, so that's going to fix it to be 10 to the power negative 12. So that is your pico already. So it's a matter of finding, this is 2,260, not 226. It's this number, 2,260. I forgot to include the 0 in there. So divided by 2.5 and 4 pi and 9, and it should be 8. Can you guys check that for me quickly? So basically, all you're supposed to do is take 2,260 and divide it by 2.5 times 4 times pi times 9. Okay, because everything else is fixed in terms of the powers. Again, which is really a very important skill that you need to develop. First, work with the powers, because that gives you the ballpark where the number needs to be. Okay. Now, you know that this number, now you're going to plug in. It's much easier to plug in these numbers in a calculator than have to worry about how does my calculator use the power? Does it use an E? Does it use a 10? And then you're spending a lot of time working with the powers unnecessarily because you can do them quickly by hand. So did anybody do this algebra quickly?
Yeah, I'm getting.
What did you get, Justin?
I'm getting 7.9931.
Is this 8 or not?
Yeah, it's pretty much 8.
Okay, picofarad. Again, the reason why this is that different is because of the fact that we used rounding in here. Actually, it's 6.1 in here. So if you really put a 6.1 in here, and so if you actually, it was not even a 6.1, 6.1.9, so it's a 6.2 actually. So if you are careful enough, I had a Professor Bruckner in grad school who was a Nobel Prize laureate, taught us atomic physics, and he was meticulous about this number like crazy, and he wanted to match them to the point. So actually, it's better rounding to this number is 2,262. So Justin and everybody else, try this number now. Is it better than the first one? Because I rounded that number down. The first one was 7.9931. How does this number now look like? Come on, guys. Is it better or worse? Or the same? It's all about doing.
I think it's somewhat the same. It's off by decimal or so, but pretty much the same.
How same was it? 7.993 what? One
I
still?
put it in my calculator again. I got 8.0002.
8.00. How many zeros? 3 or 2?
3.
2. Okay, this is actually an improvement because this is a lot better than actually this is off by the third point in here digit. This one went to the fourth digit, okay? Before you saw a difference between the first and the second. Anyway, picofarad. The point being is that they are the same. Here is a way, and the reason why I'm stopping in here and having my time with this fun stuff is because I always ask you to check if it makes sense and check your result and all of that. These are two different ways of finding the same answer, albeit they're somewhere connected up there. But the thing with it is, this is one way for you to check your answer. This is one way. Since we found V and we know what Q is, we just went to the definition of what C is, just Q over V. We found an answer. Now, different way of doing it is actually using the definition for the capacitors. Actually, not definition, derivation that we ended up with at the end for the parallel plate capacitors, which was this one. And this too should give me the same answer. Now, if I find a big difference between the two, that means I made a mistake somewhere. That means something went wrong somewhere. You guys understand?
Yeah.
Okay, very good. So hopefully you guys again are doing these things. So let's look at problem 51 now. Problem 51 has this nice, beautiful geometry. And this is what Marcela's advice will be really, really handy. Okay, if we don't do it, we're going to be in a nightmare. We're going to spend a lot of time in here. So I'm going to draw these lines like this, because I'm having difficulty drawing on the screen in here. Okay, I pick up another color in here. And I'm going to draw a capacitor in here. And another capacitor in here. Obviously, this is not correct, okay? You need a spacing in here. So, okay, let's draw it standard, and down the road, when I'm lazy about it, we'll draw it this way, okay? So let's be careful and meticulous and do that thing right way. So we have a point A. We have one capacitor. This is how it's supposed to look like. We have another capacitor. And then at this point, we have a junction. And in here, we have a capacitor and another capacitor and another junction. And in here, we have only a single capacitor and another junction in here. And we come back to point B. Okay. This capacitor is 8.6. This capacitor is 4.8. This capacitor is 6.2. And this capacitor is 11.8. And this capacitor is 3.5. The biggest caution that it may throw you off big time in your answers, and you're going to lose points, valuable points in an exam, is the fact that this capacitor is all in microfarads. Okay? But if you work this way, you're dealing with small numbers, I mean manageable numbers, I should say, then having to have 10 to the negative 6 here, 10 to the negative 6 there. And that is exactly the purpose of this plan that was mentioned by one of you guys last time. And now we're going to tackle it that way, okay? So what they want us to do is, so notice in here that I have this two in series, and the combination of them with this one, they're in parallel, and this two, they're in series, and the combination of this two with this whole thing is actually a series, okay? So let's find how to find things in here. They give us the voltage between A and B to be 12 volt. So the difference in pole voltage between A and B is 12 volt. How much height we need to go in voltage is 12 volt, exactly. And then find the total energy stored in the network. So for that, typically you have to find the equivalent capacitors. So we're not going to do it for this problem. This is what we're going to do. We're going to reduce this to just a single capacitor. For that, this is the plan. From this point on, this is what you got to do. You're going to go to the innermost and work your way outside until you combine them all into a single capacitor. Okay, do you guys understand? So it looks like I have a complicated geometry here. Okay, I have a complicated geometry here. That is the innermost, followed by this 2, and followed by the whole thing. Okay, so the innermost, I'm going to call it C1. Oh no, what did they call it in here? Did they give them? No, we're going to call it C1. Once we have C1, we will have C1, whatever its value is going to be in parallel with 3.5. Once we have that, it's going to be, so this is going to be C2 now at the end when we come out with it. And at the end, it's going to be the entire C equivalent, okay? So that is basically the plan. You hit it right in the heart, and then you start coming out until you zoom out completely. Do you guys understand how this works?
Yeah, that makes sense to me.
Okay, very good. So let's go to the innermost. The innermost, I have 2 in series. So C1 is in such a way. Let's keep it in blue. C1 is in such a way that is 1 over 6.2, 1 over this plus 1 over that. The whole thing is inverted. So 6.2 plus 1 over 11.8, and the whole thing is to the -1. Don't forget that micro stuff, okay? So this is going to be in a microfarads. You see how there is no 10 to the -6 or 10 to the negative whatever, and everything is 10 to the -6 anyway. So when you invert it, it's going to go upstairs. So right now it's 10 to the power 6, actually, if you do it this way. But don't forget to the -1. So at the end, this is a number. So if you punch it into a calculator, this is going to give me, it should be less than the smallest. It should be less than 6.2, okay? So again, I have 1 over 6.2 plus 1 over 11.8, and the whole thing is raised to the power -1. The reason why I'm doing that is because they are in series, okay? 4.06 microfarads, okay? Because they're in series, okay? Now the business of C1 and 3.5, they're straight out in parallel. So C2 then is equal to just that C1 plus simply 3.5. Don't forget your microfarads at the end in here, okay? So this is 4.06 plus 3.5, so it's going to be 7.56 or 7.6 roughly, okay? So 6, 5, 56, and 3 plus 4, that's 7. So again, because they are in parallel, it's only 1 R. Okay, that's why I just added them. Now I'm done with C2 being in series with the 8.6 and the 4.8. So the entire C equivalent is 1 over 8.6 plus 1 over 4.8 plus 1 over C2. The whole thing is raised to the -1. Don't forget that business of microfarads again. Okay, so what I have in here is 1 over 8.6 plus 1 over 4.8 plus 1 over C2, which is 1 over 7.56. The whole thing is raised to the power -1. Don't forget that step, okay? I see many people who lose points that way. They think actually C equivalent is just the sum of the inverses, and that is not true. It's the inverse of the sum of the inverses, okay? It's the inverse of the sum of the inverses. And that is because it's in series. So in this case, my calculator is giving me 2.188, which is 2.19 or roughly 2.2 microfarads, okay? So this is the answer for the capacitor, okay? So this is the C equivalent. They didn't ask me for the C equivalent, but I need it for the following reason. Let me tell you what that is, okay? Because now this is how the circuit look like. I have an A, I have a B, and the VAB is equal to 12 volt, okay? and I have a charge sitting in here on one side and a charge sitting in there. This is my C equivalent. So I have a charge of Q and I have a charge of a negative Q sitting in here. So I can find that charge of Q if they ask me, if they ever ask me what it is, but I can try to find actually the energy now. The energy now, remember from our lecture, from chapter 24, if we go back into the lecture, it's Q squared over 2C, or here. Remember I said it's very important to remember this expression? This is the energy, Q squared over 2C. If we know the charge, but we don't know the charge, we know the voltage and the capacitance. It's just 1/2 of C times V squared. So we're going to use that result instead. So the energy now, U, is going to be 1/2 of this C equivalent times the voltage squared. It's 1/2 times the C equivalent is 2.2 microfarads, and the voltage is 12. But don't forget you're squaring it. So it's going to be, okay, 2.2 squared, 2.2, not squared, I'm sorry, 12 squared times 12 squared, which is 144, divided by 2. It's 158.4. So the answer is 158.4 micro, I have a volt in here squared, microfarad times volt squared, which is joules. So it's a microjoules. You see how we did not even bother to write that power whatsoever from the beginning to the end, and we found the answer. Okay. So this is 158.4 microjoules. So that's how much energy is taken from that battery that provided that 12 volts. 12 volts is a regular car battery, by the way. Okay. So now, the energy stored in the 4.8 microfarad. So they want also the energy stored in here, in this guy. Now, here is a question for you guys. We just found the total energy to be 158 microjoules. Is the energy in the 4.8 going to be more or less than 158? We have the energy overall for all of these capacitances stored in all of them combined is 158. If I just calculate the one for 4.8, is it going to be more than 158 or less than 158?
Wouldn't it be more since the value for that single capacitor is a lot bigger than the overall capacitance?
Hold on, let's a second. The capacitance is more, you're right. This capacitor is 4.8 microfarads, whereas the equivalent capacitor is 2.2 microfarad. But the point being, just think of the energy, okay? Combine all of these guys together. Combine the 8.6 energy stored in it, combine the energy stored in the 4.8, combine the energy in the 6.2, combine the energy in the 11.8, and finally in the 3.5. That is the total energy. It's 158, okay? Would the energy in a single one of them be more or less than the overall energy stored in every one?
Oh, I get what you're saying. It wouldn't be more.
It would be less.
Yeah, it'd be less.
Very good. Does everybody agree with Byron, or do you guys agree that the energy need to be less because overall it's 158? Everything combined is 158. Does it make sense to expect that around the 4.8 is less?
I'd say so, yeah.
Okay, very good. This is a very important point when you're doing calculations. You need to think this way. Ignore this stuff about the, yes, the 4.8 is bigger. As a matter of fact, because this whole combination has another problem also. For the equivalent capacitance, which is 2.2 microfarads, looks like it's smaller than the smallest, smaller than 3.5. Don't read too much into it. Don't say that, oh, this is again the fact that we have them in series. They are not in series. These are not in parallel. This is a combination of both. So that analysis business of before that it has to be smaller than the smallest for the case of the series and larger than the largest for the case of the parallel works only if you only have purely series or purely parallel circuits. That's one thing. The other thing also is the energy overall must be more than the energy of any single one of them. It doesn't matter which you pick. That's one thing, number one. Number two, it must be the sum of all of them. So if I manage to find this energy to be so many microjoules, and add to it this energy, so many microjoules, and add to it this energy, so many microjoules, and add to it this energy, which is so many microjoules, and add to it this many energy, which is so many microjoules, at the end of the day, I should have 158, to be more accurate, 0.4 microjoules. So no matter how I do it, it has to be less, okay? That is basically the bottom line. This is how you check your work. This is how you're actually checking to see if it makes sense from the big picture. Forget about the math and the algebra and all of that, okay? So we need to find the energy. For that, I know that there is a charge Q in here, and there is a negative charge in here, overall of Q, that somehow split itself between this side and this side, okay? Because this is a junction now in such a way that this charge is the sum of the other two, okay? So somehow, this is the same Q on the other side, negative Q. This was a neutral, so this must be positive Q, and this is negative Q. That same Q on this side must have split itself in here, Q1 and Q2, in such a way that now I have negative Q1 and positive Q1 in here. And this is basically how the structure in here. Obviously, Q1 and Q2 are not necessarily equal, number one. Number two, their sum is equal to exactly Q. But in here, the Q is the same. That is the Q that is drained from the battery. So this is the total charge that is drained. So I need to find that Q, okay? So the Q that is drained, Q, is equal in such a way, remember, we have a C equivalent here. This is the same Q here too. That is actually this Q. Where this voltage in here between A and B is equal to this Q that we're talking about, that we want to find, divided by C equivalent. So from here, we can find this Q as just the product of the voltage times this C equivalent. So this Q is equal to C equivalent times the voltage, and the voltage is simply equal to 12 volts. So this is 2.2 microfarads times 12 volts. That is equal to 24. Let's do the math in here. Which is it? 12 times 2.2. 26.4 microcoulomb. Again, we're not dealing with anything. We're not putting any powers in here. They are included in that symbol in there. Marcella, are you here with us? Maybe she stepped out a little.
No, I'm here. I just couldn't find the unmute.
Okay, very good. Now, this is basically the trick that you mentioned. So it's a very powerful one, and we've been using it, and it's a clean answer this way. And it's prone to, we make less mistakes that way. Okay, that is basically what we're doing now. Okay, so that's an excellent point that you raised last time. So anyway, so the Q now is 26.4. It's the same Q sitting in everywhere. So now, since we know the Q sitting on this battery, so it's a matter of just algebra to find that energy. So the energy on this 4.8 simply would be this Q, which is, what did we say? 26.4 microcoulomb squared, divided by 2 times the capacitance, and the capacitance is 4.8 microfarads. Okay, so we need to do that energy, and we should find it less than 158.4, okay? Because if we don't, then we have a problem that we need to fix. So the energy stored in the 4.8 microfarad and the 4.8 the capacitor is 26.4 squared coulomb squared divided by 2 times the capacitance. The capacitance is 4.8 microfarad. The micro and the micro squared cancel. I'm left with a micro coulombs squared per farad squared. That's actually joule. So this is going to be a microjoule already. So there is no need to do anything else. So the only thing I have to do is take that 26.4 and square that and divide it by twice the capacitor. The capacitors in this case is going to be purely the number, not the whole thing with the micro. So 2 times 4.8, and that should be less than 158. As a matter of fact, 72.6. Okay. So as expected, the capacitor, the energy in that capacitor is 72.6 microjoules. If you're curious, trying to find how much energy is stored in the 8.6, it's the same charge divided by 2 times 8.6. So it's going to be less because the denominator is going to be more. So this energy is going to be less than 72. So as a matter of fact, so we can quickly do that. The energy in the 8.6 is going to be the same charge, which is 26.4 squared, divided by 2 times 8.6. And the energy is going to be in microjoule. So I took care of that micro stuff and all of these things. So it's going to be how much? So it's going to be the same number, except change the denominator into. I know they didn't ask that question, and you're probably wondering why am I doing this? Because I want to prove a point in here that this is actually 40.5 microjoules, okay, which is less energy in that 8.6 capacitor. So now we are almost 112, 113 microjoules. So we still have about 40 microjoules to split it about among all of these guys. And now, before you do that, you really either have to find the voltage across these guys, and find once you do find the voltage, you can multiply it by this one. You can find how much energy is in this one, and then split the other energy between the other two guys. Or you can find the charge Q1 and Q2 and use the same formula that I've been using. You will find that it's going to be the sum of the remaining energy. Okay. So if you're curious trying to find the 3.5, the 3.5 should be less than the difference of this two between the other ones. So look at the voltage in here. This is a very, very important question also. The overall voltage from end to end is 12 volt. This is exactly 12 volt. If I want to find this voltage only from this point to where this junction is, do you think it's going to be more than 12 or less than 12? So this is the junction. So up to this junction, do you think the voltage, because from A to B, it's 12 volts. From B, just down to the junction, to this junction, is it more than 12 volts or less than 12 volts? What do you guys think?
I'm thinking it'll be less than 12 volts.
It should be, because if I add this height to this height, I should get 12 volts. So this is definitely is not zero, first of all. It should be something. Then I can combine it with this guy to add up to 12 volts. It's like going from the first floor to the 7th floor, going by the 2nd floor or by the 3rd floor. So going by the 3rd floor, you're going to go, first of all, 2 flights, and then the remaining difference between the flights. Okay, so it's exactly the same thing with the height. So how much voltage drop between these ends? So it's the voltage drop between here and there, and the voltage drop between A and B. This voltage drop is simply Q over C, which is Q over 8.6. This voltage drop is Q over 4.8. So I know how much voltage drop between these ends. So Q remember, is we found it to be 26.4 micro coulomb. So this drop alone is 26.4 divided by 8.6. And that 26.4 divided by 8.6, both of them micro and micro cancel, by the way. This has a micro coulomb and this one has a microfarad. So it's going to be a coulomb over a farad, which is just a volt. So again, we don't need to deal with that power, divided by 8.6. So that voltage is 3 volt drop. So there's a 3 volt in here already. So the remaining in here from here to here is 12 volts. So So let's find this voltage drop again, which is 26.4 divided by that 4.8. And that should be, so I'm going to use the same formula again. Just because I'm lazy, and change the denominator to 4.8. So it's 5.5 volts. So from here to here, it's 5.5 volts for a total drop of 8.5 volts from here. So this drop in here must be the difference between 12 and 8.5, which puts it at 3.5 volts. Okay. From here, I can find this energy, which is just equal to 1/2 of 3.5 microfarads times this voltage drop squared. So it should be voltage drop squared. This should be less than, again, the difference between this 158 and 72 and 40. So it should be a number less than that difference. So if this difference was 40 joules, microjoules, this difference should be less than that. So let's find it, okay? So we said it's 1/2 of 3.5 times 3.5 squared. Man, it's 3.5, not 0.35, 3.5 cubed divided by 3, divided by 2. So it's 21.4 micro. So the energy in here is actually 21.4 microjoules. You see how the energy now is adding up? 21.4. There was some, what is it? Forgot in the 4.8, 72.6 and 40.5. So the number is adding up tiny by little to get to 158. You can do this too now. You can find the energy stored in both of them or either one of them. In both of them, it's just going to be the difference between the overall and minus all of this, guys. Okay, I know these questions are not asked in this problem, but I just want to show you that all of these problems are manageable now, albeit it requires calculations, but you can handle them. Okay? Yes? If you are in doubt, please come back to this same video again and follow the calculations. It requires practice. It requires you doing it, okay? A lot of times when students in Physics 4B, Physics 2 get to this point of the class, they find it the most enjoyable part of it. Some of them even to the point where they change and become electrical engineers and go to the electronics. And that is because of this part. So, because they seem to be liking it. Although when you go to electronics, you're going to be dealing with nonlinear circuits. You're going to be dealing with the diodes and also transistors and other things, okay? Which is fun, which is still fun. Semiconductors, basically. Okay. Problem 53. Any questions? Problem 51, I think we did it more than we killed it, actually. Problem 53. Problem 53, I'm going to draw it now. So we have point A. We have a capacitor C1, and then followed by another capacitor C3, and then somehow connected to another capacitor C4, and another capacitor C5, back to point B. And between these 2 points, there is actually another capacitor in here, C2. Okay, so this is how your circuit looks like. The voltage between A and B is 220 volts. Okay, so that's the height in voltage. Okay, that is VAB. What is the equivalent capacitors? They gave you C1 equal to C5. C1 equals to C5 equals to 8.4 microfarads. And the rest of the capacitors is C2 and C3 and C4. All of them just half that quantity, basically C1 over 2, or 4.2 microfarads, okay? So this is basically what we know about all of these capacitances. And they want you to find the equivalent capacitors. So we're going to work our way from the furthest point down, again, from the innermost. This is the innermost. These two guys are, oops. Are you guys still looking at the same screen, or did you lose it?
It's
We're
back to
looking
the
at the
notes.
same.
Okay, so it went to something and then came back. Sorry. Okay, so they are actually in series because it's one following the other, although they look like they're in parallel. They're not. Okay, it's this capacitor connected from end to end to the other one, and that's it. They are not. There is no junction in here. There is no split in here. It's the same wire actually. Okay. So in this case, the equivalent capacitor is going to be C equivalent is simply 1 over C3 plus 1 over C4 to raise to the -1. But if you notice that C3 and C4 are the same value, so it's just twice either. It's 2 times C3, for example, to the power -1, okay? Which makes it, at the end, C3 or C4, it doesn't matter, to the power divided by 2, which is half this quantity, that's all, which is 2.1 microfarads. So now this is how the circuit look like after I do that. The circuit look like, again, this portion is still the same, except now I don't have this 2 anymore. I have their equivalent capacitance, which is just that 2.1 microfarads, which is in series with C2, and C2 is actually equal to 4.2, twice as much as this one. So again, C equivalent for this last 2 now, I probably should call them number 1 and number 2. So this is C equivalent number 2 between this 2 now, this 2 inner 2 most is just the sum of the 2, which is just the sum of C2 and this C equivalent of order 1, so of inner 1. So which is actually 4.2 plus 2.1, and this is equal to 6.3 microfarads, okay? So now we don't have this anymore. What we have really is this capacitor in here. 1 over this just capacitance, which is 6.3. That is the equivalent of all of them up to that point, 6.3 microfarads. Which brings me to the last configuration. Now I have C1, then immediately followed by the 6.3, and then immediately followed by 6.5. I could really have them like this. C1, then the 6.3, then C5, and this is the point A, and that is the point B. This is exactly in series too. So now the C equivalent is going to be 1 over C1 plus 1 over C5 plus 1 over 6.3. And again, C1 and C5 are the same, so it's going to be just twice of either. So the equivalence now, the entire C equivalent, which is really what we're supposed to do, the entire C equivalent is going to be simply 1 over C1 plus 1 over 6.3 plus 1 over C5. And these two are the same. So it's going to be to the -1, by the way. It's going to be 2 over C1 plus 1 over 6.3, and this whole thing to the -1. And which puts it at 1 over, or 2 over, if you want to put it 2 over, 8.4 plus 1 over 6.3, and the whole thing is raised to the -1. And remember, the answer is going to be in microfarads, okay? Because I'm not dealing with that micro in there till the end. So again, 2 over 8.4 plus 1 over 6.3, and the whole thing is raised to the -1 power. So this is, according to this calculator, is 2.52 microfarads. So this has answered the first question. What is the equivalent capacitance for the network? Calculate the charge on each capacitor and the potential difference across each capacitor. Okay, so let's go and redraw the shape again to find everything, okay? So we can find what the entire charge is. So now we can find what the charge is. So because we know what the C equivalent, this is how the circuit look like now at the end of the day. That's the purpose of the C equivalent, to bring it into this shape. So now we know how much charge is sitting on this side and on this side. So Q in this case is simply equal to C equivalent times the voltage between A and B, okay? So the entire charge, Q, total basically, is going to be equal to 2.52, microfarads times the voltage, and the voltage is 220 volts. So, and that is equal to this number times 220. So it's 554.4 microcoulomb, okay? So this is how the circuit look like now. Let's redraw it again, the same circuit. So we have A, this is 554, by the way, microcoulomb. And the capacitance in here is C1, then followed by this points in here. Did I have the circuitry drawn differently or what? No, that's correct. That is correct, okay? So, and then I have in here. So this charge in here is 554. This is negative 554 because that's exactly how much it should be from end to end. And this capacitance in here is C5. This is C2. And this is C3 and C4. Okay. Now we know the voltage from A. Let's call this point C, and this point is D, okay? We know this voltage drop because we have the charge and we have the capacitance. So this voltage drop between A and C, VAC, is simply equal to the charge divided by the capacitance. So it's 554.4 microcoulomb divided by this capacitance, and this capacitance is an 8.4 microcoulomb. So this voltage drop is going to be this number divided by just 8.4. And this is 66 volts. So this is 66 volts in here. Okay. So we know the charge and we know the voltage between A and C. How about this point? That too is 66 volts for the same reasons, because the charge is 554 and the capacitance C5 is the same value. As a matter of fact, C5 is 8.4. So there is a 66 volt too in here. Okay. So I need to add a number. So I drop 66 and then something, and then 66 to go back into B. So this is basically the math. Okay, I know we still have some time. So let's do that. So the difference in potential VAB basically is equal to VA minus VB, which is equal to VA minus VC plus VC minus VD plus VD minus VB. Does this, okay, forget about everything else. If you just walk into this class, you have never heard of electricity and magnet capacitance or anything like that, and you saw this expression, and somebody writes this expression to you, VA minus VC plus VC minus VD plus VD minus VB, does this equal to VA minus VB? Yes or no?
Yes.
Yeah, I mean,
Isn't it the sum of the distance?
Sum of basically the voltages, which is the distances, which is absolutely the same thing. So what we're saying in here, this VA minus VC, that is 66 volt. Okay. VD minus VB, that is actually also 66 volt. We just found them. And this whole overall distance is 220 volt. So I need to find VC minus VD. VC minus VD should be 220 minus twice 66. Okay. So VC minus VD, that drop in potential, need to be 220 minus this 66 and this 66, another 2 times 66. So this drop in potential need to be 220 minus 2 times 66, which is 88 volts. So there must be an 88 volt in here from C to D. Make sense?
Yes, it makes sense.
Okay, very good. So we know how much voltage drop. 88 volts, I'm sorry. so that we add them up, it comes to 220 volts, okay? Now, the question is, how much charge do I need in here? I know already the capacitance C2, and I know that the voltage, so I can find what Q2 is. Q2 simply is equal to C2 times that voltage drop of 88 volts. So C2 is given to be in this problem 4.2. C2 is 4.2 microfarads. So it's going to be 4.2 times 88, and whatever it is going to be a microcoulomb anyway, because I'm not going to deal with that. So 88 times 4.2. Now here is a question for you. We know the overall charge is 554. When it hits the junction C, it splits. Some will go toward this side and some come to this side. So C2, I mean the charge on C2, which is Q2, is it going to be more or less than 554? What do you guys think? The charge that is sitting in here, that came from this side, when it hits the junction C, it's going to split. Part of it goes to C3 and the other part goes to C2. And then it's going to recombine again in here to 554. Is it more or less than 554, the one that is sitting in here?
Shouldn't they be the same?
Now it's going to split because part of it, it's like you have 60 students. Once they reach a point in here, some of them have to go one way, some of them have to go to the other way because there is a charge conservation in here. Because if it's all of it in here, then there is zero charge in here, which makes it nonsense because that means there is no voltage drop in here. Okay. So some of them must go this way and the other some must go to the other way. So question for you guys is it going to be less or more than 554? So the sum that goes in here is, I'm going to call it Q2, by the way. The sum that's going to go in here is going to be Q3. I know that Q2 plus Q3 must be equal to 554. So do you expect Q2 to be less than 554 or more than 554?
Less, since it adds up to 554.
It must, by conservation of charge. So again, when you're solving problems like this one, be mindful of this tricky things. There are so many of them. So you have to pay attention to this, all of them, okay? Because that's going to help you make sense or not make sense. So again, 4.2 times 88, I find 369.6, which is 370 microcoulombs. 369.6 microcoulombs. As expected, it's less. So if you're asking how much Q3 went to the other side, you have 60 students, split themselves, 40 went this way. So how many went to the other side? It must be just 20, yes?
Yes.
But this is absolutely just the difference, which is 554 minus, what is it? So we have answered, in a sense, the charge in here and the potential in here. The potential on C2 is 88 volts, and the charge is 369.6, okay? So that is the answer to Q2. So we're answering the problem and discussing it in the same time. So we want to know how many went 554.4 minus 369.6. I'm not being careful with the sig figs, okay? I know that. So it's 184.8. So this guy is 184.8 microcoulomb. Must go through this side. Again, there is a negative 184.8 in here, and there is a positive 184.8 in here, and there is a negative 184.8 in here. And when you add up this 369, there is a 369.6 in here. When you add them up, you're going to recover the 554.4. Okay. So 0.4 in here. Okay. So how much? Now we know the charge on C3, which is 184.4, and we know the charge on C4, which is 184.4. The only question that is left is the voltage drop on both of them. Since we know the charge and the capacitance, so we can find the voltages on both of them. So the voltage on V3 is simply equal to Q3 divided by C3. Q3 is simply equal to 184.8 microcoulomb divided by C3, and C3 is one of those capacitances that are 4.2 microfarads. The micro and the micro cancel, and I have the answer in voltage. So Now here's the question for you guys. I know from C to D, there is an 88 volts, but I can go this way. For example, on point E, this is this point. So this must be dropping from C to E on V3 and dropping on C to E to D, that is on C4. That must add up also to 88. So if I find the voltage in here and add it to this one, this number, it's the same as falling from this side, okay? So let's check that. I know the voltage on V3 is just 184 divided by 4.2, 184.8 divided by 4.2, and that is 44 volts. So we know how much voltage in here already. It's 44 volts. I expect this number to be exactly 44 volts because I want to add them up so that they add up to 88 volts. So let's check this number. C4 is actually equal to C3. C4 and C3 are the same, and the charger are the same, so the answer also is going to be the same. So it's V4 is equal to Q4 over C4, and Q4 is the same number as Q3. And C4 is actually the same number as C3, and the answer is 44. Indeed, 44 plus 44 is 88, as expected. Checks. Does this problem make sense to you guys?
Yeah, it makes sense. You just have to know what numbers to plug in and the differences from A to B, B to C, and C to D.
This is circuits in their glory, okay? So you guys are really, hopefully, you're going to go through all of this and make sure it makes sense to you, and you go through the algebra and you don't miss any of these things, okay?
Number 1 in the book for chapter 23 is a really good practice problem. It took me like 2 hours to solve, but it helped me understand why each thing was each.
Okay. From chapter 23, you said, or 24?
23.
Oh, that's a chapter from before this one. Okay, no problem. We'll come back to it at some point, okay? Because we still have about 15 minutes and we need to tackle the last problem. Oh, actually, we have still 2 more problems, man. Okay, that's fine. We can do them. Okay, so problem 57. Did I mention problem 57 is also one of the problems that we're supposed to do? Let me check. Yeah. So that is 57. Okay, so we still have 2 more problems. Sorry. So let's tackle this 2 and then we'll see what we can do. Okay, problem 57. Problem 57 says there are 3 capacitors having capacitance of 8.4, 8.4, and 4.2 microfarads, okay, are connected in series with a 36 volt difference. So basically I take 3 capacitors, so you have an 8.4 and an 8.4 and half of that, which is 4.2. And you put them across a 36 volt capacitor, 36 volt voltage drop, basically from end to end, okay? The question is, what is the charge on the 4.2? The 4.2 or any other charge is going to be the same charge because they're in series. So the fact that they're in series means exactly same charge, okay? Period. So if they ask about that, it's anywhere in between them. So the first thing I need to find is C equivalent. And the C equivalent in this case is given to be 1 over 8.4 plus 1 over 8.4 plus 1 over 4.2 to the negative 1 in microfarads, of course. Obviously, 1 over 8.4 and 1 over 8.4 is just 2 over 8.4 or 1 over 2.4. So this is the same thing as saying that this is 1 over 4.2 plus 1 over 4.2. And when you combine that, it's going to be 2 over 4.2, which is just 1 over 2.1. And the answer then is C is 2.1 microfarads. And it is less than the smallest one of them, exactly because they are in series. So now the charge, since we know C equivalent and we know the voltage, the charge now, Q, is going to be the charge times the capacitance, C equivalent times the, charge times the voltage times the capacitance. So C times V between A and B, and this one is 2.1 microfarads times the voltage, which is 36 volts. And you multiply 36 times 2, that's 72 plus 0.6, is it? 72.6? Let me check. No, probably. I don't know. Can't do that fast enough. 75.6. 75.6. Oh yeah, you have to add 3.6, not not what I did. Okay, sorry. So it's 75.6. You're right. Okay. Micro coulomb. Okay. So this is the charge sitting on the equivalent capacitance, and it's the same charge on all of them, including the 4.2. So this is the charge on all of them, actually, not just on this one. So there is a 75.56 in here. So there is a 75.6 microcoulomb, and there's a negative 75.6 microcoulomb, which makes it here a negative 75.6 microcoulomb, which makes it in here a positive 75.6 microcoulomb, and in here it's a negative 75.6 microcoulomb, and in here a positive 75.6. So it's the same charge on all of them because they are in series. Okay. So once you find this on C equivalent, which you need to find it because you can't tell just by looking at the three of them how much charge. Unless you do the C equivalent, then you can tell, because you know the entire voltage. You don't know the voltage on any of them, okay, but you know the entire voltage. So we found the charge. What is the charge? What is the total energy stored in all the capacitors? Well, the total energy is simply equal to, in all the capacitances in this case, is equal to U total 1/2 of C equivalent times the voltage squared. Again, it's Q squared over 2C, but that C then it's the same thing as the C equivalent, okay? Or 1/2 of C equivalent times the voltage. Since we found the C equivalent, we can use that. So it's 1/2. What is that? Why is this doing it today? Man, why did it close on me? Things are crashing. Things are not good at all. This computer is. So the energy total now is equal to 1/2 of C equivalent times VAB squared. So it's 1/2 of 2.1 microfarads times the voltage squared, which is 36 squared, by the way, volt squared. And the answer is going to be microjoules. So I'm not going to convert that. So I'm going to just multiply the two and be done with it. So it's going to be, again, 0.5 times 2.1 times 36 squared. And the answer is 1,361 microjoules. If you care about it, it's actually 1.3 or 1.4. 1.36 if you want to microjoules. Okay, that's how much energy is. No, I'm sorry, not micro, milli. Now we have to be careful since I used that. So the U total then is actually 1.36 millijoules, okay? Because I have 1,000, so it's kind of not right to keep that micro in there, okay? So that's how much energy. It's a lot of energy for these capacitors, okay? The capacitors are disconnected from the difference potential. So basically at this point, we remove the battery. We disconnect the battery, okay? Turn off the switch. So now it's disconnected. They then are reconnected in parallel with each other, charged plates connected to the other. What is the voltage across the capacitors in the parallel combination? So this is what they do. They took this charges and they put them, these capacitors, and they put them like this now. They were careful for them not to discharge. So initially there was a charge Q sitting on each and every one of them, and this charge now needs to be rearranged, that's all. So there is a Q1 on the capacitor C1, there is a Q2 on the capacitor C2, and there is a Q3 on the capacitor C3, so that the sum of the charges now need to be the old charge. Q1 plus Q2 plus Q3, this needs to be exactly the old charge that was sitting in the circuit. So the charge needs to be redistributed in this case. And that charge was 75.6 microcoulomb. So if I add them up, it needs to be 75.6 microcoulomb. So basically, that's what they how they arrange them. Furthermore, this potential difference in here, whichever way you calculate it, this is Q1 over C1, which is Q2 over C2, which is Q3 over C3. This is the same potential between the ends, and that's exactly what we're supposed to find. So the potential is Q1 over C1, which is the same thing as Q2 over C2, which is the same thing as Q3 over C3. Now, because they are in parallel. Parallel means same voltage. Qs are not the same necessarily, and they are not. That's exactly what happened to them. In the series, though, same Q, same charge, but the voltages are not the same. They add up to 36 volts. And here, the voltages are the same in the parallel. That is the difference between a series and a parallel. Series, same charge. Parallel, same potential. And it's the same potential everywhere, okay? So now I have this equation between Q1 and Q2, and this equation between Q2 and Q3, and this equation that has between Q1 and Q2 and Q3 that I need to solve for them. So basically use whichever equation to find Q2 and Q3. So I'm going to eliminate everything and express them in terms of Q1 or Q3. Actually, it's much easier because I know C1 is equal to C2 is equal to 8.4. And I know C3 is actually half of that, which is 4.2 microfarads. So if I look at this expression in here, I know that Q2 is equal to C2 over C3 times Q3. Obviously, C2 over C3 is just equal to 2. You can clearly see from C2 divided by C3 is just 2. So this is 2Q3. And I know also that Q1 is equal to Q1 from this equation, from this one and that one, the last one. It's C1 over C3 times Q3. And that too is the ratio of 8.4 divided by the ratio of 4.2. That too is 2 times Q3. So now I go back into this equation that Q1, which is 2Q3, plus Q2, which is 2Q3, plus Q3 must add up to 75.6 microcoulomb. From here, I can find what the charge Q3 is. It's 5Q3 is equal to 75. So Q3 is equal to 75.6 divided by 5. Remember, it's in microcoulomb. So 75.6 divided by 5. And that gives me 15.12 microcoulomb. And the others are just twice as many. So Q2 and Q3 will simply be equal to this number times 2. Okay, which is 30.24. If you add up this, twice this, which is 60 plus 15, that should be 75 microcoulomb. So that's the charges. Now the energies is easy. So what is the total energy in this now stored in the system? You have to find the energy per charge, okay? You have to find the energy here and the energy there and the energy there. And the energy here, it's Q1 over 2C1, Q1 squared over 2C1. This energy is Q2 squared over 2C2. And this last energy is Q3 squared over 2C3. Okay, once you do that, you add up all of the energies, and I'm going to leave it to you to do that, and also check to see how much it is compared to the previous energy. There was so many joules in there to begin with, and you will find that this energy is less than that. There is a loss of energy, and the loss of energy is due to the rearrangement of the charges. When you had them in there and you put them now so that they moved, there is a current that they must have caused to go around, and that current went into heating the wires. And we will get into that topic in chapter 25 and 26. So this is really a prelude to that chapter in terms of what's going on. Because in here, you're asking, what happened to the energy? I started with 1.36 millijoules, and now I have less. So why is that? It's because energy is lost, okay, due to something else. So this is that problem. I know we still have 1 minute, but I'm hoping that you guys will stick around at least for another 5 minutes or so to get problem 59 going. Yes?
Sounds good.
Okay, so problem 59. Okay, very good. So remember that you're supposed to finish this problem part of your task, okay? Check, verify, and finish all these calculations. That is what you're supposed to be doing with this kind of sessions, okay? That is why we have them. So now, they give you a circuit that looks kind of big circuit, okay? So let me draw that circuit. I have C1, 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 and the insert C2. So I have 3 on top here. And there is nothing, there is actually 1 in the middle there too. And there is a bunch of them this way too. So this is, and then there is in the middle and here, there is another one. And there is another one in here. And let me pick up the blue in here. Obviously this drawing is not correct because you need the capacitor in here, C1. 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 And there is another one in here. And there is another one in here. And there are 2 capacitors in here, C2 and C2. Okay, so that's how the circuit looks like kind of a alpha circuit. All of the C1s are C1s are 6.9 microfarads, and all of the C2s are 4.6 microfarads. 6.9 that is, okay? And compute the equivalent capacitance of the entire network. Okay, here is what we do. We have this 3 are the innermost, and it's the same value. So I'll have to add 1 over C1 plus 1 over C1 plus 1 over C1 and invert their value. So it's going to be 3 over C1 inverted, so it's going to be C1 over 3. So this, if I remove them, I replace them by basically another capacitor, which is a third of either. So it's going to be 6.9 divided by 3. 6 divided by 3 is 2. 9 divided by 3 is 3. So it's going to be 2.3 microfarad. All of the 3 are gone now, okay? And the 2.3 combined with the C2, and that should give me 1 over 2.3 plus 1 over 4.6 inverted. No, I'm sorry, they add them up. What am I talking about? These are in series. These are in actually in parallel now. So we just add them up. So I need to add up 2.3 plus 4.6, and that is exactly 6.9. That is 6.9, exactly like C1. So basically, after we remove this entire section, we have another C1 in here. Okay? And again, a C1 and a C1 and a C1. So we're going to get rid of them, and we end up with C1 over 3, which is 2.3. And 2.3 microfarad added to this one, which is going to be another C1. So again, C1 in here. And C1 and C1 and C1, the entire C equivalent as if it's just C1 over 3. That's all, which is 2.3 microfarad. So you see how fast you can do things if you get into it? Because there is symmetry in this problem. That's why it was easy. So at the end, the equivalence is just, but you come from one end and you work your way toward the other one, okay? So that is C1. C equivalent, this is C equivalent is 2.3 microfarads. So, and then compute the charge on each of the 3 capacitors nearest A and B. So we need to find when the voltage is 420 volt between A and B. So now we need to find the charges, okay? So the charges are going to be the following. It's easy for the first 2 and hard for the third one. So the charge again is going to be equal to, remember it's C times V, and C is the C equivalent and the voltage is the entire voltage. So that's going to be the total charge actually. And the total charge is going to be drained from the battery is 420 times this number, 2.3 microfarad times 420 volt, and that should be 2.3 times 420, and that is 966 microcoulomb. That is the charge sitting on C1 and on C1, both of them, but not sitting on C2. The C2 is only part of it because, again, it splits in two. Part of it goes here, and part of it goes for the rest of the circuit, okay? So basically, if this was 966, Q2 goes here and Q3 goes here. So I need to find what that Q2 is. For me, I need to find what the voltage between C2 is. I know this entire voltage is 420 volt. I know this voltage now since I know the charge 966 microcoulomb, and I know the capacitance C1, which is 6.9 microfarad. So I know the voltage between this end and that end, which is supposed to be 966 microcoulomb divided by 6.9 microcoulomb. Again, it has to be less than 420 because overall is 420. So this voltage must be less. So if we check that, 966 divided by 6.9, it is 140 volt. So there is 140 volt in here. This is also 140 volt because it's the same value of the charge, which is 966 microcoulomb, and the same capacitance. So there is also 140 volt. 140 volt and 140 volt, that's 280 volt deducted from 420. That too is 140 volt in here. Okay? So there is 140 volt between C2. And I know C2 is just 4.6 microfarad, so I can find the charge now. So the charge on Q2 is simply C2 times 140 volt, because 140 plus 140 plus 140, that is 420 volt. Is it? Yeah, it is, okay? Because 300 plus 120. I'm doing the math quickly, so again, you guys, your job is to check this thing. So C2 now is 4.6 times that, 4.6. It should be less than 966 because 966 splits itself part to the rest of the circuits and part to C2. So 4.6 times 140 volt. So that is 644 microcoulombs. So 644 microcoulombs. And the rest, which is the difference between 966 and this number, went to the rest of the capacitors. So this is basically the problem. And they want you to find the voltage drop between these points. Here. Since you know now the charge, which is 644, and you know the overall charge, so you can find that the Q3, which is 966 minus 644, 966 minus 644, that charge is 322. So this is 322 microcoulomb. Now you can find the voltage in here. This voltage must be the charge divided by C1. So that voltage need to be less than 140 volts because this is 140 volts. So this must be less because we have to go all around to come back to it. So again, 322 divided by 9.6. And that is 33.5 volts. So there is 33.5 volt in here. And there is 33.5 volt in here, which makes it add up to what, 66, 67 volts. 67 volts, and I need to add them up to end up with 140. So again, that is going to be the difference between those numbers. 67, yeah. So that is the sum of these numbers to get to what we need to get, okay? Because it's the same voltage too, because it's the same charge. If there is 322, there is a negative 322 and a positive 322, and the capacitances are the same, okay? Makes sense to you guys? So once you find that, you find this voltage in your own business. Make sense, these problems?
Yeah, it makes sense.
Very good.
Go
So go ahead.
Oh, I was just gonna say I'm going over it once more. Definitely would help because this did go very quickly, obviously because of the time we're lacking. But yeah, it makes sense.
Very good. So it is highly recommended that you go through all of them step by step. Come to this recording to make sure it makes sense to you, so know what next step. Now, if you're confused or you don't know what to do next, please let me know so that we don't I don't want you to be stuck looking at a problem for a long time. I want you to really be moving along. And basically, when you see a circuit, you know exactly what to do. You know exactly what to do. Come exam time, I don't want you to be thinking of a way of doing it. I want you to be doing, okay? Make sense?
Yes, Professor.
I will see you guys at 5 p.m. tonight, okay? To do the lab.
Okay. Do we need the lab printed out beforehand?
No, you never need it printed, actually. You can just work with it electronically. You don't need a printer.
Okay. Sounds good. We'll see you at 5.
See you guys. Goodbye.
All right. Bye.